So as promised, this is an opinionated view on what tensors are. For the experts in the room, no, this won't cover everything, but there's actually a reason I don't want to cover everything, is that I don't want to be overwhelming. To the serious expert who disagrees with what I'm doing, I'm going to say the following. There's a reason. I'm trying to set up a conversation about best practices where I think that we're being a little bit thin on details. So to set that off, let me start with an example. In 2006, the Netflix Corporation started us out on a weird journey of merging mathematics with more and more data sciences. And they did this by a competition. They supplied a list of users and their movie preferences. So about 100,000 users, and they had grades for the movies, and I don't know how many movies, zillions of movies, and they also put up a cash prize of $1 million. Don't get excited, it has been paid out. It was paid out in 2009. They had some intermediate prizes for people who made progress. What was the question they asked? They asked the contestants to provide missing data. You can imagine the value to Netflix is that not everyone has had time to watch every movie, and not everyone who's watched every movie has bothered to grade every movie. So there's some missing values, and Netflix would like to serve up the next movie recommendation for you so that they have a happy customer. Now, I suspect that if you're able to monetize a better algorithm, it'll make you more money than $1 million. So my advice in a contest like this is don't give away your answer, start JFlix or whatever other thing you need to do to be the competition.
Are you going to fund that?
Yeah, I'm not going to fund it, Martin, but I'm happy to like see what movies we can put on there. There'll be like these YouTube videos of us with puppets. People will love it. So, anyway, that was the. But it turns out there's actually a competition that happened the year prior. Actually, maybe I'll tell you about this. This is a conceptual view of the Netflix tensor. I will give you a more thorough view in a minute. So these are two actual movies. Well, one is Star Trek Voyager. It's a movie. It's a TV series. Cube 2 is a real movie, and I thought it was appropriate for what we're doing here. It's actually Cube 2 : Hypercube. Enjoy the Wikipedia article on it, because I think it'll make you never watch it. Anyway, so here's some samples of how Jericho, Tony, and Valentine voted on these movies on a scale of 0 through 5. And you can see that Tony didn't even bother to grade Cube 2. And I think I have a grade having never watched it. So, okay. So, but this is the one I want to actually talk about because I think it provokes us to a conversation. There's actually a competing, much more popular competition that happened in 2005. Same idea, a bunch of missing data in the tensor, and the goal is to crowdsource people coming up with the missing values. Okay? It involved tons of people, most of them volunteers, and in fact, a lot of them even paid money to join. That's even better than giving away a cash prize. It was this, right? So how is a Sudoku puzzle any different than the Netflix problem? That's the problem I want to pose to you when we consider tensors for a minute. If the Netflix prize is really, I give you a table of values and I fill in some of the values and you use that to predict what goes in the missing places, then Sudoku should be like the Netflix puzzle. And yet I don't think that's valid. I don't think that most of us really draw an equivalence class between them. Now, what are some of the reasons that we wouldn't say that Sudoku and the Netflix prize are in the same class? I might say it's scale, one thing, right? This is small, but you can make a bigger one or make many of them. I think there's a deeper reason, and I think it gets at the reasons that I generally don't like describing a tensor as a grid of numbers or a multi-way array. I think that undersells what we actually want to talk about when we come to a conference on tensors. And so I'm going to start out by articulating in a concrete way why these are two different problems and why we don't typically call the Sudoku puzzle a tensor, but we do call the Netflix prize data a tensor. Okay? So, data science is an emerging thing. Every department is facing the need to either add this to their courses or consider eventually creating a data science department. What is data science? Well, I don't know. What was computer science 50 years ago, right? It's an evolving theory, and we're going to be adding to it as we go. Some of the sources that I like the most, the one I like the most is really blunt. It says, try to get something useful out of a large data set. This is out of some authors of a recent article from MIT. This is my version of that same statement. I'll try to make it more precise, more mathematical if I can. I'm going to say that data is whatever we bother to measure or calculate from the measurements we have. That could be colors, you know, I look at the color blue. It could be words that I write down. It could be frequencies of events. It could be measurement in the classical sense of holding a ruler up. It could be any number of symbols or letters or numbers. And so if I look at a clock, I can see some data. So in this drawing of a clock, I can see that there's some sort of a font that's being used. It's not like a Roman numeral, for that's part of the data set. There's a color of a red hand and a yellow background. If I was looking at an actual clock, I might hear something, like the clicking of the sounds. The numbers are there, the clock maker I could maybe make out. These are all facts that I can see in the data set. Now, that's not enough to do any science. You need a question. So let's ask a question of the clock. What time is it? Reasonable question to ask of a clock. And now we can get to the question of what data science is really trying to tease out. This give me something useful. Something useful means I have a goal. My goal here is pretty simplistic. It's a training exercise. I want to know what time it is. And so now I look at the information as the subset of the data used to answer my problem, or at least study it. So here I ignore things like colors and fonts. That doesn't help me understand what time it is. I focus purely on the parts that tell me time, which are the numbers and the hands and where they are. Okay? So I throw away a lot of the data to get the information out of this. Well, here's a different version of the question. Do I trust the clock? Maybe I don't. If I don't see that the second hand is moving, I start to doubt. If I don't hear the clicking sounds, I start to doubt. We start to see that the data has shifted, the information has shifted because we changed the question. I want you to think about that. The data is out there. All this data is some infinite list of all the things we could measure or calculate. All of that's available to you, but not all of it's informative because you have a question in mind. Once you have a question, you filter down to something smaller. And I'm leaving out questions like feasibility. That turns out to be another layer upon this. What can you actually get to? Can you measure with the precision you need? Those kinds of questions also come in, but this is not an applied math class. So what I want us to do is to think about the tensor versus non-tensor question in a slightly different way. I want to think about not whether this could be a tensor in some hypothetical scenario, but whether the scenario that we're facing when looking at these data sets would be informed by the tensor perspective. And if it's not informative to look at it as a tensor, then I set aside the tensor label. So when I do Sudoku, I don't use tensor methods, and so I don't think of Sudoku as a tensor. If you do use tensor methods on Sudoku, I think you're working too hard. You should buy a little book from the library that says how to do Sudoku in sort of straightforward logic puzzle ways. But if you want to use tensor methods on Sudoku, no one can stop you. Okay. So now let's try to get into the more conceptual, concrete ways of thinking about the Netflix tensor as a tensor. The most likely way that we see tensors like this is that we think of this in the univalent format. What we mean here is that every row is a vector. So I could plot these, and I've plotted one of them in dotted lines because I don't know what to do with the missing data, right? Maybe I just omit that vector, I don't include it. Maybe I put an artificial value. Here I put an artificial value of 0. Maybe you should think of it as an equivalence class of the whole horizontal line of all the things that it could be that would substitute in for the missing value. There's lots of ways to have a mental model of this, but the idea is that every row is some vector in some large vector space. And usually it's not this small. The Netflix tensor was surprisingly small in data sets, but huge data sets exist. This is actually the data set. I mean, of course, it's a very small sample of it, but when you look at the Netflix data, this is what you see. And this is a warning for those of you who decide that you're going to take your skills and apply them in real life. You will not see these tables. They're not given to you as tables. They're given to you in random formats. They're surprisingly, I mean, there are really cool formats like JSON and stuff like that that computer scientists have invented to make structure show up in the data set. And almost no one uses it. They use comma-separated values. They just put white space between words. And so, you know, I don't really know why. But this is the preferred model, is to just write down everything in order. And so you can see there's some sparse notation here, like instead of putting a user's name, they've anonymized it as a number. And then here there's whatever the movies, those are numbers that you have to look at some catalog and get the information out of that. So one of the things that I find frustrating as a mathematician who's not a computer scientist, who's not trying to do data science, is that I'd like to experiment on a tensor, but when I download a tensor, it's this. And then I have, you know, a couple days work to parse this into actual data that I can do data science on or something. That's a problem that I have to live with, but hopefully the tools get better over time. But never, the point is, you have to assemble this yourself. You should think of all tensors in real life as being emergent properties, not just usually handed to you as a block of data. You're going to have to interpret how you want to see this as a tensor. And just to make this a slightly bigger competition here, is what happens in real life is that you collect other data and you cross-reference. So Netflix gives you some rankings of these people, and then you know what? You're resourceful enough, you go buy from a data broker some more information on Jericho. You find out that Jericho is a low-income person living in the US, so forth. You add that to your table, now you can make better predictions because you've lumped them into some. Is that good for society? I'm not here to judge, right? You can change all these data points to things that are, you know, altruistic and whatever you want to work on. I'm just trying to demonstrate how you could evolve this data set and how it often is. When you do this, however, if you start merging together completely unrelated parts of the data to make a larger data set, it might help you inform yourself about what kind of genres people might be wanting, but it's a little hard to convince yourself that you should be mixing the actual movies with, say, income and location. Those seem as separate parts of the data set. And so this is where the real tensor type, you know, the cubical thing that we have a mug to represent comes in. We try to keep that data separate. Now, it's still that every row is one piece of the data, but instead of being one vector that's sort of moving around in some space, it's now some position in this grid. And you add in all the values for each individual, and you get this big, possibly high-valent description of your data. This is the array description of the data. It's just a representation of the data. The data is still the files we had before, but now we're in our heads modeling this as data, numbers just living in a cube or a hypercube or whatever cube 2 is. So this is a trivalent demonstration of that. Okay? Let's put some names to that just so we can talk to each other. These names are all out of common textbooks, and you will always find another textbook that uses a different name. Okay, so these are all valid, but not the only ones. So the main one is you have an interpretation, some way the data is actually given to you, and the interpretation is I'm folding it up like this. There's these sides to the tensor. You need some way to describe that there's sort of sides to this. I call these axes. Many people call them modes or legs. The physics community likes the word legs. The engineering community likes the word modes. The mathematicians like the word axes. I mean, and that's not universal. That's just what I've noticed in patterns. Okay? So those will be different axes of our tensor. If we want to talk about all the axes together, we sometimes talk about that the frame or the frame of reference. Other names apply. Now the one that's tricky is this one and this next one. Many of us swap the words around or use the same word for many things. And that's because of a standard problem. When I draw a box like this, and I ask you what's its dimension, you would say two-dimensional. It's a box, right? But if I say it's a 3x4 note card, and I say what's its dimensions, you're bound to say 3 and 4. Because there's two notions that you have in mind. One is the dimension in the sense of like how long this is and how long that is. Another one is how many parameters you needed. And to use the word dimension two different ways and try to do mathematics is bound to not only confuse, but to make actual errors. For this reason, I use the Russian convention of calling this outside thing valence. So the frame here is two-valent or bivalent, and the dimensions I will reserve as 3 and 4. Not everyone does that, but do try to be kind to your listeners and your readers by telling them what you're using so that they have some chance to hold on to what you're saying. All right, back to our Netflix data, try to figure out what's going on here and the differences. There's several types of data you could give. I'm just going to articulate a few here that are relevant to the discussion we have. The first type of data we might have, I would just call static. What you see is what you get. That's like going to a bus stop and looking up what bus you need to get on to arrive by 7 o'clock at your next station. You should do nothing to that data. You should not start multiplying the rows of the bus stop to rescale the numbers to 1. You should not row reduce the bus schedule, okay? Now that's data, right? Under the definition I've given that you can do whatever calculations to the things you have, it is data to row reduce the bus schedule. But I don't call it information because it won't help me arrive on time. At least, if that's how you're using the bus, we should have a little chat in the hallway after this to discuss how you might get on time without using row reduction. Okay, so I consider that static data. What you see is what you get. You just read it, you look it up, you get the values, okay? Permutational data is data that can come in whatever order. So I often have students' information in a roster, and sometimes it's sorted alphabetically. That's irrelevant. It could be sorted analphabetically. I often do sort things analphabetically. If you've noticed the website, all your names are analphabetical. As a Wilson, why should I always be at the end of your list? Max? So there are plenty of us who know what it's like to be at the end of the alphabet. So it doesn't matter if you change the order, the information's still there. So is still informative to permute the data. That's permutational data. Monomial data, you can think of monomial matrices. This is when you can rescale and reorder. Then it would make sense to and that's often the case when you're trying to compare, say you have like frequency analysis, you have some sentences, one person describes they like this movie, they leave a review, and they just say, well, it was the best movie of 2007. And the next person says, the same thing, but very flowery. Now, if you just do a frequency count of their favorite words, one person will have a bigger vector than the other because they said the same thing over and over. So you might rescale that by normalizing the vectors. So you can compare, are they different actual content, or are they just one person's more flowery than the other? So then rescaling that kind of data makes sense. That's monomial data, data that you still find information after rescaling. Linear data, which is the one I care about the most, is when you can also combine the data. You combine it with a recipe. And I like the word recipe because it reminds me of food. And food has linear combinations, right? If you ask yourself what's the nutritional value of an apple, you go to some authority. Here in the US, I'd use the Food and Drug Administration, so I downloaded this data, and I would read off what are the properties of an apple. They did some experiments in a lab. But if I'm making a fruit salad, I do not have to send my fruit salad to the lab to find out the protein. What do I do instead? Well, I have a recipe for making the salad. I know how many apples and how many strawberries and whatever else. And I go to the data sets for those raw ingredients, and I multiply by the percentages that I used, and then I get the recipe turned into the nutrition of my salad, right? So this is a case of trying to generate data outside of what we already collected using a recipe. This is when we're really into the tensor land. This is when we're looking at the Netflix data. Let's see how that would make sense. In the Netflix data, let's imagine something that might be informative. The perhaps most boneheaded goal you could have is you take the data you have and you just take everyone's average. If everybody ranked Cube 2 really low, you're not going to recommend it to a random person, right? And if everybody ranked Voyager very high, then you might recommend it, even if you know nothing about this other user. If it's completely missing data, you'll put the averages in as a just first punt. But what is an average if not a linear combination? And you might even finesse that. You might discover that you have some people who are kind of like leaders in a field, influencers of some form. You might weight their average as more influential, giving them a weighted average. Isn't that just a recipe? It's just changing the recipe for who's important to that formula. So you're taking the data and you're contracting it to create a new piece of data from the data that you have. So the data is not the point. The tensor that Netflix gives us is the way to generate new data. That's our real goal. With Sudoku, do you find any value in adding one row of Sudoku to another? Maybe Martin does. He's playing one right now and he's trying that technique out. So some of us who are a little bit more like low-level Sudoku players, we don't add rows to other rows. So you're starting to see the difference, right? The key thing is if we add the word of what's informative to the goal is fill in the missing pieces. In Sudoku, it's not informative to start adding things. It's not informative to take the determinant of the Sudoku matrix, right? But it is informative to our Netflix puzzle to start taking combinations. Maybe not everyone, but some combinations start to matter. So the tensor methods start to be influential for this, but not for the other. So that's what I'd like to make sound by the end of this talk, is what does it take to actually describe data that is tensorial? And keeping in mind that when it comes to applications, often we have to draw a deciding line. We have to first put on the table, what's the question? Without a question, I don't have a definition of information. And therefore, I can't tell you that's not part of the data set. You absolutely can row reduce a bus schedule. But should you? So there's a sociological question first before you run into the tensor networks, right? Okay, we said this. I don't see the determinant being useful in the Sudoku puzzle. Prove me wrong. Say Netflix, things are important. Okay. Averaging is a good way to test. Let's see how good you did. Okay, we did one of these. We did the last two. Maybe we should just take a second and ask the person sitting next to you what you would rank as like on each of these things. If somebody gave you a phone book, would you consider that something you reorder and it doesn't matter? What about rescaling, combining? Take a minute, take a row, convince each other.
Yeah, I would more or less yeah, you would have to give
What is combined? Professor Wilson?
Yeah,
What is combined?
Oh, well, add them and rescale them. Sorry, it's a shorter word to fit in.
Yeah. I don't think.
That was about the same
Image definitely.
Oh, and you can combine
if you I've seen instances where people actually like combine something like
imagine
they have like vector spaces images and then you want like an eigenbasis for it and you like combine and generate all the possible images instead. So I think you can combining
in other expressions, Sudoku.
I don't know how to play
Okay.
You can change it.
I have answers for all of these, but they have to come after you ask me a question. So I will reveal none of my answers, but you have to find me afterwards and ask me a math question, or actually any question at all, and then I will reveal my answers, okay? But I think you need to explore this yourselves, is my point. The one that I find the most interesting to have conversations on is this image one right here. There's very deep conversations can happen with that. Ones that are upsetting to our signal processing folk. Of whom I have many friends. I drink with them on Tuesdays. Okay. So the summary point at this point is this. This multi-way array view of a tensor is not bad. It's useful, but it's not what makes it a tensor. That's just a way to conceptually organize the information. And in fact, it's not even how it's stored. Even when I said that things are stored as a bunch of words or whatever, once it gets compiled into the machine, it still isn't stored that way. Like there's like boundary limits of how wide the memory is, and the machine decides I'm going to just write this all as one big flat array and just stride my way through these arrays. And like there's so much happening that is not about this cubical shape that it's embarrassing that that's what we define it as in the start of our papers. That's a piece of it. It can be useful in your concepts, but that's not what's making it a tensor. What's making it a tensor is that we have this notion of contraction. When we use contractions, when we add recipes to the data we have to create new data, and that's actually part of the conversation you're trying to have about that data set, you're definitely in the tensor regime. Okay? If you're not using the contractions, it doesn't mean you can't call it a tensor, but it's a little forced. You're basically telling me about Sudoku. And that might be a fun problem for a different kind of mathematics. That's the bone I wanted to pick with the community. Now that I've picked it, let me try to make this a little more precise. So, next part of this is to put some math to the words I've said. Full screen. Okay, we'll get as far as we get with this one. What does it take to do contractions? Now that I've made the stage that contractions are essential to be doing tensors, what do you need for contractions? What does it even mean? Well, it's easy in a salad. We just do this intuitively. We just see the recipe said put 16 strawberries in, or maybe it weighs it in grams or something, whatever it is that's appropriate. We just rescale that one by that amount. We just keep adding those pieces together, and that's straightforward. But the key I want you to remember is that there's two pieces of data. There's typically the table itself, the thing we think of as this multi-way array. That table will be what we use to sort of get the story started. That's the thing that the FDA or your users or whatever have provided for you. The rest is us adding different recipes to learn something about it. Create something like our own menu. Create a substitute for what's an ideal person in the Netflix movie community. You know, stuff like that. Okay? So we have this table T, and that will be the tensor in this storyline. We have some recipe vector, which in this case I'm going to say the recipe is my fruit salad recipe, and then I'm going to contract them together. And just to match how we do matrix multiplication, I'm going to, for this minute, put this one on that side. But I'm not going to use just matrix multiplication because I want you to observe that there's a little bit more hanging on here. I actually have a three-dimensional tensor. It's not layered like a tensor in a cube because that's not how it's stored anyway. This is all trying to visualize data. So I want you to think that whatever u times t is, it's not quite matrix multiplication or vector matrix multiplication. It's something bigger. It's tensor contraction is the word. Yes?
Wait, sorry, is the u supposed to be v?
The U is V, yes.
Okay.
It's just that this font doesn't have good handwriting. So, that might be true. So yeah, so this U and that V are the same, and so we contract them. Okay, so that's just notation for whatever the product is, okay? And there are formulas for it. You can see what you do. Scale the row and add it to the next row. You'll see more in a second. But what I want to stress now is that it's not just one thing that we do. We often contract in many directions, and that's where the cubical array sort of picture really does help us, because it reminds us that I could add this way or this way or this way. I have different directions, different axes that I can do this in. So often what you have here is you want to work out what is the cost of buying these ingredients. That would sum across. And then I'll put it on the other side, just to keep it convenient. So you can see that I'm going to run out of sides here if I'm writing left to right. So eventually, what are we going to have to do? The dreaded subscripts come in. We start subscripting everything, and all this stuff becomes what's known as the nightmare of index calculus. I have a slight suggestion on index calculus in a slide later of how to improve so you don't have subscripts on subscripts as much as possible, but I've never avoided subscripts entirely in the tensor world. And that's just the pain that we have right now. If we all learn how to draw in 3 dimensions with our pencils, we'll do much better. But until then, all right, now there are some rules. Because I can contract on the rows and the columns, I could get into a world of hurt. Right? I could contract this way and wind up with one answer, and this way and that way and wind up with one answer. And in real life, flowcharts do that. But mathematicians like predicting things, so they would like to say, let's not do that. Let's assume that the kind of things we're doing are so polite to each other that it doesn't matter which way we go, you get to the same answer. You could say the diagram commutes, but the word that's actually used in the literature is entropic. So if you look at algebraic books, there's a reason I'll just show you, it's in the slide. So I'll just point that out, okay? No, it's not the word commutative. It's also not the word associative. You can think of that as parentheses, and it looks like I don't need parentheses. No, it's actually something called entropic. Entropic is because they're not actually the same operations. Commutative is something like this. Commutative is A plus B equals B plus A, right? And it's the same plus on both sides. Here, they're not the same operations that are commuting in some sense. They're different functions, they're different contractions, and so there's a different name for that. It comes out of universal algebra, okay? Is it somewhat straightforward what the cohesion condition is? You just go any side, you get the same thing. And of course then, you know, somebody at the back room could say, well then I'm not even going to take a tour around the sides, I'm going to contract all at once. And that's reasonable too. Contract both sides at once. And maybe there's even a faster program to take the diagonal than taking the 2 sides. That could happen. It won't matter which way you do it. They'll come up with the same answers.
Just curious, do you know
Yeah.
the motivation for calling it entropic?
I didn't name it. so no, I would have named it after myself or something, right? But no, I mean so in the 70s, when people were trying to work out how certain types of algebras come together in different operations, words like commutative and associative already mean something, like this. And then on top of that, they might have this further property, and entropy means disorder.
Okay.
So this means it's
like
a-
some information theory connection or something.
No, it's just the word disorder, and since the operations can go in any order, then they can be disordered, I guess that's my hint. There's another phrase that's used called medial, we'll get to that in a minute, and then there's another phrase called like distributable. There's another name, anyway, there's a paper that came out in like the 80s or something like that, which lists in the first paragraph all the alternative names for this property. But entropic seems the most popular.
James?
Yes.
Is this like popular in the 70s or popular now?
Is it popular in this, what do you mean by popular? The entropic, is the word entropic the most popular?
I haven't seen the word entropic.
That's because you're an operad person, right? Because if you know operads, then that supersedes everything. Right? So if you do this with operad theory, then you have other words. But any universal algebraist would know entropic. Even today, go talk to Petter and
There are no people doing universal algebra these days.
absolutely there are. Well then don't go to Denver. I think that we just learned is that you'll get stoned in Denver. So no, there are certainly universal algebraists. I would say that it's not the most popular type of mathematics to just study universal algebra, but there's some gems in there. So the point is not to throw out gems. So what I'm headed towards is the Davy-Davis theorem, which is the definition of the tensor product in general, and that's just done in this way. That's where I'm headed. But you're right, you have other ways to do this. You can, like modern day people will say universal mapping properties and things like this. They hide it all under some very high sophisticated things. I just think it's maybe more than, say, your clever data scientist wants to learn. So, easier to just think go in any order, for me at least. I don't know how to make those go away. Maybe they're here to stay. Okay, no, we want to go down. So here's another way to think about entropy. Entropy is you have two different operations, which maybe take several inputs, maybe they take two. And you can think of either adding or doing the operation in columns and then across, or across the rows and then the columns. And that's the same picture that we have on the previous slide. What's an example of this? Well, oh, another way to think about it, sorry. You can think of your operators as sort of like, this is operad notation now, or like operad pictures. You sort of think of your operator as a shape, and the inputs come in and they feed out to the other one. So you have these types of green operators, they feed into the yellow operator, and that would be the same as putting the yellow operators then feeding the green one. It's the same. These are all just mental pictures to give you a sense for how you can go around. Okay. And when you're building a general, say, monoidal category, this is the picture you want to keep in mind. So the main example for tensors, though, just to keep it kind of low order, is this, right? You just sort of add up in one direction. So it's easy to do when you just have three numbers, you just kind of add them up. This would be sort of just, you know, contracting with an all ones vector. But usually we think of weighted average. Oh, went too fast. I have to wait for it to recycle. So here we have some weights on each of these coordinates. We rescale by the weights, then we add along. That's contracting in one valence. Okay, so if you can contract in one valence, you can contract in two valent. So move the numbers across, then add along, right? You see the same picture? You basically move the data, you reweight the data, and then you add in the axis that you added. Okay, and this gets bigger dimensional. You can make this move all the way down, so you can contract with large spaces. These are all just visualizations. But usually we just use a formula. Okay, so the computers do this for us. Whoops. Yeah. And so just trust me, there are lots of different definitions of contractions. They're not all going to be that way. In fact, one of the things you need to do is think about how to do contractions efficiently. This is where optimization really can go deep into, like, how does a GPU work? If you're trying to think about doing tons of tensor contractions inside of some neural network, you want to do just the ones that matter and do them as quickly as you can and not wait on any new data to come in. Yes?
Just a quick question. On your last animation, your weighting is in a different direction than your summing. Was that intentional?
Did you? Okay, so if there's a mistake, it wasn't intentional. If it's correct, then it was definitely intentional. So what did I do here? So here what I was trying to illustrate was that I was taking a 3 tensor and contracting it with a 2 tensor to form a 2 tensor. So the way I was doing it, and really I should say this slightly differently. There's a different picture I would draw for myself. So I'd say that I have the data, that's the cube, has 3 axes to axis, so I, J, and K. And then here what I wanted to do was tie them together with some 2-dimensional thing to create that. That's what I was trying to illustrate, and I don't believe, I could sit with the picture and see if I did that right. But anyway, this picture will make more sense in future talks when we get to tensor network diagrams. This is another way to write it. Yes?
All of these operations look like they're along canonic axes. Are there situations where you want to do some...
Canonical axes in what sense?
Along the axes.
Oh yeah. Well, I'm using multi-way arrays because they're easy to draw a picture of where you see the axes. But of course, what's really in here is that you designate which particular columns in your data set you're counting as part of axis 1, axis 2, axis 3. Those might not be contiguous. Those could be spread out wherever they are.
But they may not all be along the columns of your data. They may be along some...
They may be...
subspace of your data.
Yeah, but you can... I'm choosing to, in my head, permute the things together to make them cubical, to make them look like a grid. Yeah. But they, in real life, could be separated in irregular states, irregular steps and so forth. So you might have a complicated formula for looking up each index, and you might want to modify that, because that may not be an efficient way to do the arithmetic. Did I get closer to the question you're asking? Yeah, I mean, in general, they're not cubical. This is just a mental model of the data, and often the data is sparse, so you never want to fill in the zeros.
I wasn't even thinking about the cubicle is about the bounds of the data. I'm
yes.
About the axes. Maybe there's something along the diagonal.
Oh, would you only want to add up some of the data set? I imagine there are applications of that. I would say that it's a little complicated to get that in the tensor model, to just only add the diagonals up. So basically, I would say that would have to be something that's outside of the standard tensor contractions. I don't know if it has a name, and I may be wrong. It may be that there's some clever way to write that up as a tensor contraction, because sometimes you can do amazing things with sums, but I don't know. Like one of the things that we do with, so a typical tensor contraction will have sum over maybe I, j, and k. It'll have the data, which is labeled by I, j, and k, and then it'll have the individual recipe vectors that are telling you how much to rescale by. Then you could decide to repeat the vector. It could be a square or cubical, and you could just use u in 3 different places, okay? So you create this somewhat specialized cubic polynomial now because you've repeated some of the variables, and so you can get different behavior out of that. But that's no longer the whole tensor. That's just one piece of that tensor. So this is creating a cubic form out of this tensor. So you really have a product of 3 u's, and you just happen to fill it in. So it's not that the definition of the tensor really takes u, v, and w, but you've specialized and used it in a special way. And oftentimes, this is an interesting object to study, these cubic polynomials or whatever, degree homogeneous polynomials. And you can go backwards. If you have such a thing, you can create one of these tensors by something called polarization. So you can go back and forth. Some information gets lost in some characteristics, things like that. Okay, what do I want to sort of finish up on here? Inflation is the exact opposite. People can debate this, and I don't really have a strong horse in this race, except to say that it is different to think about the inputs versus the outputs. And so if you're taking vectors and creating a multiplication table, then that's making output values instead of taking input values. So if you're doing this, you're doing something dual to tensors, but it's no different than, say, how a functional is dual to a vector. You can make this into a tensor as well, but these are often what we call tensor products, and the products build up rather than take down. Okay? Other notations, and this is by no means exhaustive, just standard product notations. Take any kind of notation that you've ever seen to put products together, and you basically have to clump them together somehow. And you can give it a name or not give it a name. You can use symbols, not use symbols. It's your call. Okay? I wanted to promise you something about subscripts and subscripts and subscripts. Here's a plausible way to reduce some of your subscript needs. So oftentimes what you need to do in a product that has many terms is identify some piece in there, right? Just one particular coordinate that you want to talk about. You're doing something in that position. So one way to do this is to not think about these as listing 1 through L, but just say there's some name axes. This is called labeled tensors. So if you have some list of axes that have names, and then you identify which space they're coming in. So then when I pick an axis, all I have to do is think of this as restricting the function. So if I put A, I'm saying what does it do on position A, and what does it do on the complement of A? It's the same idea as specializing to that coordinate, except that I don't have to have dot, dot, dots or subscripts, and I don't have to reorder, because all I'm thinking of is the function is partitioning the input to the output. So my function originally started on the whole set A and then gave me back vectors. And then I took A and I partitioned it into B and C. And so when I took B and C, if I restrict U to the part that's in B and U to the part that's in C, you can see that putting them together will give me back U. And that's all I need to do to keep track of the information, right? Is I tell you what's it doing on the entire domain. So I don't have to worry about subscripts anymore. I just simply say, look, that's my vector U that I'm putting into the product. When you want to get to the B axes, you just use the B part. When you want the C axes, you put the C part. And then it allows you to separate these two functions. Like this function needs to be the addition of 2 numbers in position A, and then just be the regular vector in the positions that aren't A. Or you can just unwrap it with a lot of dots. Nothing's wrong with the dots, except you sometimes get lost in notation or it fills up your page, things like that. All right, this is where I want to make sure we get to. What if we have multiple recipes? So multiple recipes means that we're going to combine them somehow. And the most natural one that most people really want is some form of distributive property. If I have a fruit salad recipe, and I also have a recipe for making, I don't know, fruit punch or something like this, and I'm going to have both of those, I take these 2 recipes, I multiply them with a nutrition chart, and that's what I ate, right? That's the nutrition combined. So I just add up these 2 values, the U plus U prime, and I add them up. So what else distributes? Well, basic stuff distributes, but basic stuff distributing actually teaches us what to look out for. So obviously area distributes, like that's the foundation of calculus. Volume does the same thing, and it's no surprise that it does that. It's more or less the definition. Okay, so it gets us to calculus distributing. We see that in calculus, just the linear rules of calculus. Okay, no one's surprised. But this next one, actually, I think it sort of surprises me sometimes. Because if we think about integrals as area, well then adding the f plus g is modifying the height. And we saw that distribute. But what about the width? I mean, widths distribute as well, right? I mean, it's like, that's a distributive law, and that's not in this formula. Where is it actually at in a calculus book? The distribution is on the subscripts, right? Two disjoint intervals distribute. And that's a different addition than adding numbers. That's a disjoint union. That suggests something. The distributive law is actually not bound to concrete numbers like the real numbers or decimals. The distributive law can distribute over lots of things. So if you're binding the concept of contraction to having a distributive operation that's entropic with its other distributive operations, the word distributive applies in lots of places that may not seem familiar, like a grid of numbers. And this is how tensors show up in a number of stranger places than you might have expected. So for example, oh, maybe this, okay. What I was going to show here was that, okay, I'll say a word about this. These are two rivers that some of you know. One of them is the Rhine River and one of them is the Colorado River. Okay, figured that was a nice combination of rivers. And what I was going to say about this is that why do we need a tensor in something as pointless as area? I mean, we all know area, and that's because there is no one who measures area the same way. Like if I measure a river, the length is in one unit and the depth is in another. I'm going to measure the length in miles or kilometers and the depth in meters or feet. I have to have a conversion because you can't make one instrument measure everything. So there's going to be some conversions, and then there's going to be conversions that are purely about which place you live in the world. And as a general caution here, this has nothing to do with whether the imperial or metric system is better, because I promise you, if you write these both down as binary numbers, they're both awful numbers. Right? The computer thinks both of these are stupid. So do not get on a high horse about which convention we should be using. That's missing the point. The point here is there is no area without parameters. You have to have this external tensor to define area or volume. That's the parameter that I want you to think about tensors as describing a multiplication table. Even for something as boneheaded as area and volume, you need extra parameters, and that's what the tensor provides. It's the way to write down a new multiplication table for this context, for that context, for the other. So you can make general analysis by saying, I'm going to study what happens when I change this tensor and not worry about the measurements I'm making. Those are the recipes people give me eventually. So just to name some of the things here, we've already talked about some of these. Tensors have to be interpreted somehow. The tensor is the thing that prescribes the multiplication. The multiplication is a bunch of axes. Together I'll frame it. The outcome is put somewhere. I'll call it a base. All right, so this is what I wanted to make sure I ended on. We're at the very last minute here, so we'll get to it. One definition of tensor. This seems to capture all the definitions that I've seen in the literature. It is flexible, and it's still somewhat easy to understand. You do what Hamilton did with vectors. You do not define a vector. You instead define a vector space. And a vector is whatever lives in such a space, right? Try not to think about a vector as a pointy thing or a list of numbers, because that's not what it always is. Sometimes it's a functional, sometimes a function in LP space or whatever. It's lots of things. But it behaves some way, therefore it gets to be called a vector. In the same way, I try not to define a tensor. I certainly try not to say it's some hyper multi-way array, because then I'm forced to use that. In fact, the Netflix tensor couldn't be a tensor if that was the definition, right? Because it's not a multi-way array. It's a bunch of separate files of text. However, if I create a tensor space which can interpret how to think of that data as this multi-way array and use it to have contractions, then that data now gets to be a tensor, because it's an element in some tensor space. Okay? So that's my definition of a tensor, is the tensor space is a distinguished term in a distributive product, no other rules, and a tensor is anything in such a space. For my life, it helps to separate this from cotensors, which is to describe the outputs of a distributive product. The outputs of a distributive product are usually going to behave dual to the inputs, so I like to call them cotensor spaces and think of their elements as cotensors. This is supported in geometry circles. It's less supported in algebra circles. Many algebraists conflate the two and treat them as equal, and there's good reasons for that. I'm just choosing not to. Okay? All right. I will say nothing about those or those. These are all different examples that come from everything from like post sets and logic circuits are all beautiful examples. You can go look up Boolean tensor if you want to see what Boolean tensors look like. Remarkable field in there having nothing to do with decimal numbers. It's all about like NP completeness and circuit optimization. It's a beautiful area. Tensors show up where you don't expect them. They just need to have a distributed product around. And you can do distribution on lattices. You can do distribution on Boolean numbers. You can do distribution on foundations of math. You can do distribution on categories. Any place that you're doing those distributions, the lessons of a tensor still apply. That's the lesson I want to take in. Do I want to say anything more here? Yeah. Okay. I'm going to take an extra minute and just do this one because this I think is worth it. So what's the point of this? If you circle back to say Netflix or Sudoku, and you take this perspective on that the point of a tensor is to have these contraction maps. The point of a tensor is to make it the multiplication table of some multiplication. What do you gain from that wisdom? So I have here just a spreadsheet. You can sheet 1, sheet 2, and it has different numbers in the table. So it's a multi-way array. But I treat it instead like a multiplication table. And here, just to help us think of it as multiplication, I've labeled row 1 not by D, but by 1. Right? And this is in a different position, so that's x, right? So I've got 1x, and then it goes into the board as 1 and x. Just labeling it in a suggestive way. It's so suggestive that you probably are factoring something in your head. What you've noticed is that x times x is minus 3x minus 2, which is that, which factors. I'm just on the algebra side now. And because it factors, I can rewrite the multiplication table like that, right? I factored it, and now x plus 2 and x plus 1 are 0 divisors. And so I took the original data set, which was clumpy, and I organized it. This, to me, is the whole point of a tensor. The whole point of a tensor is to find a recipe that simplifies your data set. And because you're allowed to add that to your data, right, you take a recipe and generate new data, you can find good vectors, like eigenvectors or things like this, that rearrange the data you have to make it look nicer. Now, where do you get good vectors? You don't get it from the data, because there's a 1,000-year head start in algebra. So you go to the algebra, you find better algebra, and you get better data. That's the power that mathematicians get to add to the tensor metaphors. If you add contractions to your data, you get to do algebra, which might simplify the data. That's the whole story, from my perspective. Now, for the rest of this conference, please take my perspective with a very big grain of salt and take everyone else's on as well. And at the end, I think you'll probably have pretty good foundations for this, okay? All right, I'll stop there. We'll have another talk here in about 7-8 minutes. So thanks for your time.